In this segment, we'll discuss Parker Veriflo single-stage regulators. We have the general purpose IR 4000, IL 4200 general purpose regulator. The difference is the IR 4000 regulator is stainless steel. The IR 4200 series regulator is brass. We also have the IR 5000, which is very good for low sensitivity and low pressures. We also have a tie diaphragm at TDR 959. We'll discuss tie diaphragms later in other modules. We also have the high pressure HPR 800 and the APR 66 regulators, along with high flow HFR 900s and HF 1200 series. We also have negative pressure NPR 4100s, NPR 959, and the dual stage NPR 735. Along with this, we have our vaporizing regulators, AVR3, which is heated with steam, and then the AVR4, which is heated by electronics. Then we have our compact regulator, MIR 700 series. The primary function of a pressure reducing regulator is to take a high pressure source and reduce it to a low pressure outlet. They maintain a stable flow pressure over the range of inlet pressures. There are different outlet pressures and different inlet pressures depending upon which series regulator you choose. The primary operation for a pressure reducing regulator is merely turn the knob in the right direction. Turning it right opens up the poppet, which creates the flow and the pressure. Turning the knob left decreases the pressure, decreases the flow and increases the pressure. We measure flow with flow curves. We measure droop. Droop is nothing more than just the curve of the line. As you increase the flow, you decrease the pressure, as shown on the flow curve. As you start to shut the regulator by turning the knob to the left, you will decrease the flow and also increase the pressure. We measure hysteresis, which is merely a certain point on the flow curve for the decreasing flow and the increasing flow. Creep is measured by, actually creep is created by the seat. The seats are plastic, so what happens here in this area, this little curve or this tick up, this is where the seat is actually started to shut the flow off, has made contact with the poppet, and the tick up actually is when the seat has reformed around the poppet, securing the flow and the pressure. Creep is the leakage across the seat again, and right in this area right here is where the seat will eventually reform around the poppet, and it will actually create the positive shutoff, and it will shut down. No more flow, no more pressure. Again, right here, the creep stops after the seat deforms enough to seal the imperfections. Hysteresis is caused by friction. There's an O-ring in this area here. Friction is necessary for the regulators to operate properly and precisely. The O-ring itself causes the friction, which in turn will cause the hysteresis. And again, friction is designed into the regulator. Supply pressure effect is nothing more than right here where the diaphragm is what we would call the balance point. So in order for the regulator to operate properly, we have to have the pressure pushing down with the range spring. These range springs come in different spring rates depending upon the outlet pressure you desire. So we have to have the force of the spring pushing down on the diaphragm. It has to overcome all the gases and the poppet. Consider the poppet spring rate as a force pushing up on the poppet. What has to happen is the force pushing down on the diaphragm needs to equal the forces pushing up, as well as whatever gas might be under here pressure-wise. For instance, if this light blue was 30 psi pushing up against the diaphragm, this range spring needs to overcome all of that pressure in order to push that poppet down. So in order to make the ballast point, which happens to be the diaphragm, I have to have as much pressure pushing down from the range spring as there is pushing up. But all these forces, gas, spring rate for the poppet spring, and then any pressure on the outlet side pushing up against the diaphragm. Once those are overcome and this diaphragm becomes the balance point, the regulator will work.